Hi. So thanks very much to the organising committee for putting on such a good conference and for giving me the opportunity to talk. I'm Tristram Warren. I'm postdoc at Oxford University, working under Neil Bowles, who's the PI of Lunar Thermal Mapper. And Bethany Eldman gave a great talk yesterday on Lunar Trailblazer. So Lunar Trailblazer has two instruments. It's made of two instruments. One of them is the high resolution HVM cubed mapper, and the other instrument is the instrument that we've contributed from Oxford called the Lunar Thermal Mapper, which I'll talk to you about today. So we delivered the instrument about a year ago, February last year. This was the team. It was a huge effort. This was the team at delivery. That black box there is the black box we shipped the instrument in over to Lockheed. So as a quick overview, LTM is a 15-channel thermal radiometer. It's got 4 thermal channels and 11 compositional channels. Don't know if the laser is working. Oh, it is. So the right at the front, it's got this pointing mirror mechanism. And then we've got an internal black body for doing calibration. So this pointing mirror mechanism will rotate about here. It will point out towards the moon for when we're doing surface observations. And then it will also point at the sky and into the internal black body for doing our calibration views. Other things to point out. So this is our optical relay path. We've got 2 focuses. So at the intermediate focus, we put our filters. You can just see them here. And then at the second focus, we have our detector. The instrument has a resolution of about 50 meters per pixel at our nominal kind of orbital range of 100 kilometers. And our detector is an uncooled microbolometer. So the main objective of LTM is to provide support for HVMQ's 3-micron spectral measurement. So HVM cubed is kind of an iteration of M cubed. M cubed obviously was a near IR spectrometer that cut off at about 3 microns because it didn't anticipate finding water at the lunar surface. So unfortunately, it's cutting off right in the middle of the 3-micron absorption feature. That led to some issues because depending on the surface temperature, the assumed surface temperature, and the thermal correction that you do, that changes the band depth of the water feature. So Lunar Trailblazer is doing 2 big things to correct this. So the first big thing is HVM cubed spectral range will go out much further, out to 3.6. So it captures all of that 3-micron water absorption feature. And the second thing is we've got our instrument, which is a co-aligned thermal radiometer measuring the surface temperature. So we will have, for the same field of view, the independent measurement of the surface temperature to do the thermal correction and provide context for the 3-micron measurements. Yep. So how is Lunar Thermal Mapper doing the temperature measurements? So like I said, it's got 4 thermal channels. Up here, I've just plotted some normalized Planck functions for different temperatures. And up at the top here, I'm showing the band passes of the different thermal channels on Lunar Trailblazer. So Lunar Trailblazer will capture all of these temperature regimes that we find on the moon down to about 100 Kelvin. And as you can see, depending on the temperature, the temperature of the Planck function, you get these different gradients at around 3 microns. And this is what's been causing the issue on the M cube measurements, because depending on the surface temperature changes the amount of thermal correction that you have to remove from the signal, depending on the surface temperature. At kind of 100 microns, at 100 Kelvin, the amount of thermal emission is so low that it's negligible, so we don't really need to remove it. So in the requirements for LTM, we're only required to measure down to about 100 Kelvin. We think from our ground testing campaign that we can go lower. We just didn't promise it in the original proposal. The other thing that LTM is going to do, so it's kind of secondary goal, if you like, is to map the composition in the mid-IR spectral region. This is kind of following on for LTM is kind of an iteration of Diviner, which flew on Lunar Reconnaissance Orbiter. Diviner had 3 8-micron channels all centered on the Chris-Janssen feature. So here we've plotted up kind of some key lunar minerals. These are from some ground-based measurements made by Kerry. And then, so Diviner had 3 8-micron channels. LTM is going to take this much further. So we'll be having 11 channels across this spectral region. And you can see we'll be getting a lot more information. So on the right-hand side here, I've plotted the convolved lab-based spectra with the LTM channels that we anticipate getting back, and the dashed lines are showing the original Diviner channels. So this will be a big step change from Diviner. So we anticipate getting a lot more compositional information and a lot more information about this very strong thermal gradient you get at the near subsurface on the moon, as well as higher spatial resolution. So we'll be able to do a lot more in terms of understanding the thermal environment on the lunar surface, something I'm very interested in. So these are our physical filters. So we have a filter mounting block that we mount all of our filters in. We make these filters in Oxford. They're thin film filters. And then this picture here I'm showing on the right. So this is prior to installing them in the instrument. And then this picture here, we're looking down through the optical chain of our instrument. So we're looking through that first pointing mirror, and you're looking at the intermediate focus where the filters have been mounted. Here I'm showing the band passes of all the filters that we measured in the lab. You can see some long wave leaks in some of the compositional channels. We get rid of these by putting a kind of blocking filter in front of them to block out that. Whoop. So we had to obviously calibrate our instrument before we delivered it. This was the best picture I could find of our calibration facility. Sorry, it's not great. But basically, this is our instrument here, sat on this kind of lever arm that rotates. Inside our calibration facility, we have kind of 3 views that we can look at. So we can look down at a black body that we keep near 100 Kelvin. That's kind of to simulate our space views. So the idea here is in our calibration facility was trying to make it as flight-like as possible, so as if we're in space. And then we have one calibration black body that's simulating space view. We have a second black body that's kind of at this angle, and that's simulating the lunar surface. So we kind of ramp that black body to different temperatures. And then we had another view to put kind of different pattern targets in front of our optical chain, and that's to kind of do some standard optical tests to measure sharpness of images and stuff. And then the other thing to note is that we also surround our instrument in this kind of cold shroud. So this black painted stuff here, and then you can't see it, but there's a shield that goes around the whole thing. That also gets cold to simulate being in space. So I'm showing here some results from our calibration campaign, just quickly. So this is our detector. This detector is an uncooled microbolometer array. We get these detectors from the manufacturer, and they have a window on them. And that window kind of blocks at about, I think it's 25 microns. Obviously, our instrument goes out to 100 microns. So we have to remove that window. That in itself is not an easy process. And then I'm showing here, this is a typical readout from our array. And you can see this kind of stripy pattern going on. These are all our filters. So this is a full frame readout. You can see 2 filters. These are our kind of high signal channels. These are the 2 that are standing out here. And then so one of the views in our calibration chamber, we can put in these different pattern targets, and these are kind of standard optical tests, both for doing alignment and for doing like sharpness and image quality tests. So I've just shown a few images here of some standard kind of like geometric shapes that are used for those tests. So the other big thing during our calibration campaign is obviously we measure the performance of our instrument. Again, I'm showing here a plot which very nicely shows the structure of our full frame with all our different filters. And over here, you can see we've got this strip. These are actually providing blocked off filters, blind pixels. They're very important for doing a load of noise removal in our signal chain. And the big standout thing from our calibration is that we do meet our requirements. Our requirements were to measure a noise of below 10 Kelvin at 100 Kelvin signal. So our noise in our instrument is temperature dependent. The lower the temperature we get, the greater our noise, just because we've got less signal. But at 100 Kelvin, we were measuring about 3.6 in our calibration chamber in terms of actual noise on the detector. This is in our longest, so our 50 to 100 micron channel, which is our best channel for measuring such low temperatures. It's quite challenging to measure high accuracy at low temperatures because of the lack of signal. There's kind of two modes that we can operate there's several data processing tricks that we can use to reduce our noise. One of those is something called time delayed integration, which I won't go into. But that will reduce our noise by a factor of 2. So with TDI, we expect to drop that noise even further down to 1.7, which is promising for kind of distinguishing, cold traps on the moon. We just haven't measured this in our calibration facility yet directly. So the other important thing is we delivered our instrument with a slightly curtailed calibration campaign because we had to get it ready for delivery. But we do have a flight spare instrument that we are putting in for a longer calibration suite. So we will actually have a flight spare instrument ready to go on potentially a next opportunity or launch opportunity. So I've just got a few conclusions. So LTM will provide co-aligned surface temperature measurements with HVM cubed. It's important to mention that Lunar Trailblazer, which is the main mission, is going to be doing targeted observations. So it's not like a global mapping system like Diviner or Lunar Reconnaissance Orbiter was, but these are targeted missions. Like Bethany said, we're very bandwidth limited. An LTM spectral range will be expanding on Diviner in terms of composition, and hopefully we'll get lots more information about the moon. With that, take questions. Thank you.
Thank you. So any questions for Tris?
Yeah, Ben Greenhagen, APL. So thanks for the really detailed information on the noise floor of the long wavelength channels. So actually I have a different question. So for the 11 compositional channels, what's the temperature range where you'd expect to have adequate signal to noise to be able to make the spectral measurements?
Yeah, so the slides have gone. Yeah, so we're only going to be able to get good signal kind of at equatorial regions. I haven't done the sums in terms of how far down it'll be, but it'd be around 300 Kelvin. It's kind of our limit.
Any other questions? Have you found that? I'll do a quick one. Sorry.
All right, go for
Have
it.
you found there was any challenges with making it sort of space flight ready? Did you have to do any trade or compromise in some of the optimizing of the science?
Well, in terms of money, I mean, we're using an uncooled microbolometer array, so you could use a better detector, but we didn't want to go down that path because it makes it a lot more costly. But I mean, yeah, we've had loads of problems. I think all space missions do, or I hope they do.
Lots of lessons learned.
Lots of lessons learned. Yeah, yeah.
Okay.
Thank you.